We have also discussed position vector, where you can see in the figure position vector P has two components, one along I and the other along j. So the position vector can also be written as P times d cap, where d cap is a unit vector along the direction of the vector P. Okay, let us look at differentiation of a vector. So in case of scalar, the traditional equation is dy by dx is, as limit delta x tends to 0, y x plus delta x minus yx divided by delta x. This is our traditional equation. So similarly, for differentiation of a vector, we can write, instead of y, you have your p vector. Now, this vector has two properties, as we have discussed before, magnitude and direction. So the vector can change in both magnitude as well as direction. So let us look at one by one, step by step. Let us say the vector changes only in magnitude and the direction remains constant. Okay. Now in the figure, we can see that the vector OP, right? The vector OP has changed to P times T plus delta T. After a small time, you have change in the vector P to Pt to Pt plus delta T. So now your delta P is parallel to Pt. So delta P, your change in, so this is equal to limit delta T tends to 0 delta P by delta T, right? So dP by dt is simply dP by dt times d cap, which is simply the change in magnitude while the direction remains the same. Okay. dP by dt is nothing but square root of dpx by dt square plus dpy by dt square. Now this is your dp by dt, and your direction vector is same as that of P. Okay, so when there is only change in magnitude, your dP by dt is simply dP by dt times d cap. We will also write this as dP by dt in parenthesis. If we use the parenthesis, that means it is change in magnitude alone. Okay. Let us look at the case where you have only change in direction only, right? There is no change in magnitude, but there is change in direction. Okay. In this case, as you can see in the figure, we have change in direction. So P at time t is here, and after delta time t, P has come here. So the difference is delta P, right? Delta P is nothing but, delta P is from this equation here, your delta P is Pt plus delta T minus P. So this is your delta P. So as delta P tends to 0, so your as limit delta t tends to 0, your delta p becomes perpendicular to both the vectors p at time t and p at time delta t. So in this case, delta p, so in this case your dp by dt will be perpendicular to p, the vector p. Okay. Now, what is the magnitude? Magnitude of delta p. So delta p is nothing but p of t plus delta t sine theta. So as delta t tends to 0, your sine theta becomes theta. So right, so delta p equals to p of t times, this will be approximately equal to p theta. So your dp by dt is equals to limit delta t tends to 0 delta p by delta t. So this will end up being, as limit delta t tends to 0, this will be p by t. So this is nothing but p times theta dot. This will be the magnitude of the vector dp by dt when there is only change in direction, and the direction will be perpendicular to p. In this case, when you have only change in direction, your dp by dt is, magnitude is p theta dot, and as we have discussed before, direction is perpendicular to p. So the direction will be along p cap, where p cap is a unit vector perpendicular to p. So now p cap can be written as, so this can also be written as theta dot k cap cross p times d cap, because k cross d is nothing but p, so which is simply omega cross p. So this is your velocity in pure rotation. When there is only rotation, you have omega cross p as your velocity vector whose direction is perpendicular to the vector p. Okay. In magnitude and direction, when you have these two, then, which is the general case, you have dp by dt as change in magnitude by dt times d cap, plus you have your, what was it we have written? Yeah, p theta dot p cap, right? So this is your translational component, this is your rotational component, right? Okay, so this can also be written as, we will write this as dp by dt in parenthesis as translational component plus omega cross p, which is a rotational